All right, welcome back, Chemistry 241 guys. We've got an exam coming up, and I know a lot of you want to do really well, so I hope this video answer key will help guide you through the packet of practice problems I gave you. And so before we get started, just a real quick note. I know this is going to be kind of a lengthy video, so feel free to just zoom ahead and focus on the things that are most confusing for you to clear up those concepts or those problems rather, and if you need to, work through the whole thing. I think these are all really good practice problems. Again, another best way to study for this exam is to go through the homework. The homework, I think, are the best indicators of the types of problems that I find most important and the things that I would definitely think are good targets for exam type materials. Again, this question answer, this problem set, is about 5 pages, a lot longer than our exam. Your exam will be about 3 pages, but still making sure you can work through these will be a great way of building your confidence for this exam. So I'm going to go ahead and dive right in, try to keep this as direct as possible. Here we've got a really neat problem that I think really connects to some of the more general concepts. So, if you're thinking about vocabulary terms or big topics that were important, these are the kinds of things that you may be expected to do. Explain them, maybe not in mathematical terms or in a specific reaction, but generally, what do these things mean? And so this is really important. So let's jump in on this one. So chelate effect, right? That was something that we talked about a while back, and really it deals with, I would argue, monodentate ligands versus polydentate ligands. And so one example would be, let's say we have a metal and we've got a bunch of aqua ligands around it, right? And I'll just pick a square planar, and I'll just say that, we'll say this metal was a 3+, and this whole thing then, since water or the aqua ligand is neutral, that whole thing is going to be a 3+, and I'm going to say replace all those aquas with amine ligands, right? And so if that's the case, I can look at the equilibrium of this and I get what? I get the same metal, right? We did not do any redox chemistry, and in this case all the aquas have been replaced with amines, right? So we have, again, 3+ total charge, plus in this case what? We've got 6 of the waters that were knocked off. Okay. In this reaction, right, we could go in the lab and we could measure this, and it's going to have some K, and we'll just make up a number. We'll say this is about what, 1 times 10, I don't know, we'll say 10 to the 6th. I don't know, I'm just making something up here. You can look in the actual data tables in the notes. I gave you some really specific examples, but I'm just going to explain it this way. And so what we could do instead is we could instead replace these aquas with something really similar, and I'm going to say, okay, same thing here. I want to try to keep this really as an analogous example as possible. So instead of 6 amines, I'm going to go ahead and change that to 3 ethylene diamines. And again, if you don't know ethylene diamine structure by now, you're behind. So ethylene diamine effectively is a bidentate ligand. I'll go ahead and draw it again just to save you a trip back to your notes. You're going to have this carbon backbone, and you've got essentially a bidentate ligand, but I would argue that looks an awful lot like amine, right? It's just we popped off one of the hydrogens and connected it to another one through a carbon chain. No big deal. But this is bidentate, really important. And we can look at this equilibrium, and you would get, again, let's keep that constant. We're going to say that we've got the tris ethylene diamine, right? So that means that would be there. And then again, since you used 3 of the bidentates, that's going to kick off all 6 of the aquas, and there you go. And so if you go measure, I would estimate, if I had to guess, that K value would be something like 1 times 10, I don't know, maybe the 12th. That's crazy, right? I mean, look at that. If you look at this, you say, okay, you can connect K, right? You know how to connect K's using the equations to get delta G. And in this case, these are all, negative values, which means they're very spontaneous. And if you relate delta G to the other thermodynamics you know about, well, you know that you have delta H minus T, which is temperature in Kelvin, right? So that can never be negative, times delta S. And that's really important. Okay, so let's look at enthalpy and entropy here. You look at this K, and you're like, oh my God, that is 1 million times more favored. I mean, look at that. Going to 10 to the 6th, 10 to the 12th, right? Six decimal places, that's a million. So if you look at what's going on here, you can say, okay, it's either being driven by delta H or delta S. And in this case, I'm going to say you're popping off water or aqua ligands, right, that are bound through the oxygen, right, in both cases, and you're replacing them with ligands that are bound through nitrogens. And so here you go. So you might argue that nitrogens are maybe going to bind more strongly to oxygen, but it's really not that big of a deal. So enthalpy is not going to be a big factor here. It's effectively equivalent in both cases. The bonds we formed, the bonds we broke are roughly the same. So no, enthalpy is not going to be a big deal. But here, if you look, you have one of these, so 1 plus 6, that's 7 things. Over here you got 1 plus 6, that's 7 things. So entropy, pretty much the same. However, look at this bottom one. You've got 1 plus 3, that's 4 things. Over here you have 1 plus 6, that's 7 things. So if you look at that, 4 things going to 7 things, I would argue that is an increase in disorder, which means the sign of delta S is positive. And if you increase the value of delta S and you're going to subtract it, that will drive delta G down to greater negative values. Greater negative values means more spontaneous. So it must be entropy, the disorder going on, that drives this forward and gives you that 1 million times enhancement in favoring the products. And so here, again, chelate effect is a thermodynamically driven thing here by entropy, right? Entropy is a state function, and so you can look at that and make that explanation. The other thing you can say is, what is the actual chelate effect? Well, here now you see that actually binding two of these places, right? This bidentate or polydentate, it comes from the Greek chelos, right? Meaning to grab or to bind, like a claw, right? And so these guys can bind onto metals and give you much more favorable binding interactions than the analogous monodentate version. So I hope that's helped. If not, go and check out your notes, because it's all right in there in gory detail. This next one probably be a little bit quicker. Here we say, okay, well, explain why this complex, or this is actually coordination compound, is a colorless compound. Well, we don't care about the calcium. That's a counterion. So we do know they're 2 times positive 2, so that means this whole thing needs to be a, oh goodness, that's terrible, 4 minus, right? So 4 minus, right? And why is that? Because negative 2 for oxalate times 3, right? And then so that means that this zinc has to be a positive 2, because you have negative 6 plus 2 gives you that negative 4, which is bound neutralized by the calcium. So we only want to look at the complex. And so if we know that we have zinc and that's in a 2 plus form, this is where you have to go to your periodic table and to be able to do an electron configuration, and that would be argon and 3d10. So if that's the case, okay, this is an octahedral, right? There are 3 bidentates. That means you have 6 binding sites, which means coordination number 6, which tells you that's an octahedral. And you know the splitting diagram, right, for an octahedral at this point. 1, 2 up top, 3 down at the bottom. Z squared, x squared minus y squared, xy, xz, and yz, right? And so that will give you your delta O, because it came about through an octahedron. Now remember, the other thing you can remember is that you only have to worry about high spin and low spin for D4 through D7, so don't even start talking about that. That's not a case here. We've got D10, which means, let's go ahead and fill it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, notice that all the d orbitals are filled, which means that if light were to come in and hit this complex, there's no way to promote a d electron. You can't move. So if you can't move, you can't jump, you can't absorb a photon of visible light, and if you can't absorb any visible light, it passes right through you, which means you will be a colorless compound. No color in the visible spectrum. So pretty neat. This would also hold true for what? It would hold true for something like a titanium 4+, which would be a argon 3d what? Yep, 3d0. And if you have an absence of any electrons in the d subshell, they can't jump. No light gets absorbed. So both the D10 and the D0 case will give you colorless compounds. Pretty cool. All right, this lanthanide contraction. We talked about this so often. So the observation that you would see is something like gold, right, and silver. They have almost identical atomic radii. And why is that? Well, if you notice, if you go from silver, right, which is a 4D metal, and gold, which is a 5D metal, there's one big difference. And when you do the electron configurations, you need to prove it to yourself. You begin to introduce the 4f subshell. And the f orbitals are kind of crazy looking. And if you look at them, they kind of look like, remember the d orbitals? They were the four-leaf clover looking things. Well, that's not what an f is. An f looks like a six-leaf flower or six-leaf clover, if that even makes sense. And you look at something like that and you go, okay, you begin to kind of point away from the nucleus. They kind of spread out. And when you do that, when you put these core electrons or these inner electrons further away from the nucleus, they shield less. And so if you have your f orbitals, right, f orbitals, they are very poor shielders. And if they are poor shielders, that means that the Z effective that the outer electrons feel is increased compared to what you would expect it to be. So you would expect, right, gold to be much bigger than silver, but that's not what we see. And so what happens is, by gold having these 4f orbitals, the electrons are spread out. They do not shield the outermost d electrons, and so those outermost d electrons are pulled in more tightly than you would expect, and it appears like there's some kind of contraction going on. They don't get smaller. Don't say that gold is smaller than silver, but you would expect gold to be larger. However, you actually measure a nearly identical atomic radius, and so the reason for that is because you have a higher Z effective due to the poor shielding of the f orbitals. So anyway, we talked about that. And what it means is it means that gold and silver will actually have very similar chemistry because they will share common oxidation states, and their oxidation state to size ratio are going to be really close, which means they will have very different chemistry often than the 3D, which would be copper in this case. And so that's something that you can take away from that. All right, last one for this longer first problem. Circle the element with the higher ionization energy. Remember that ionization energy, especially the first ionization energy, is essentially the energy to remove a first electron from a neutral atom. And so what do you notice here? You've got chromium and copper. And chromium, right, is in column 6, and copper is in column 11. So that means as you go from left to right on the periodic table, this one's further down. And you should remember that as you add protons, you're increasing the nuclear charge, and you're only adding electrons to the valence shell, and they're not very good shielders. Only core electrons are really good shielders, so that means that you're not shielding very well. So that means the effective goes up as you go from left to right across a period or a row of the periodic table. So copper is going to have a higher Z effective, which makes it more electronegative, which means it's going to be harder to remove an electron. So if it's harder to remove an electron, that first ionization energy goes up. So copper would be an element in this case that would have the highest first ionization energy. There we go. Relates back to some very simple periodic trends. All right, so this next page. Now we're getting into more of the specifics, right? The idea of thinking about certain skills that we've talked about, and these are really important. And so naming, right? Naming has to be down by now, and so if you're not confident in your naming skills, you got to go back and revisit that. And so this first one, let's think about what's actually bound in the complex. Ethylene diamine is a 0 charge, and now you have to think about what is the charge here. Well, you know that nitrate is -1, and you have 3 of those, so in order to balance that out, that cobalt better be 3+. So let's go ahead and write that out. Again, this is a cation, so you don't need to worry about any special names. You just say, I've got ethylene diamine. Now, ethylene diamine is a bidentate ligand, so you have to use a special prefix, right? So it's tris. And we have ethylene diamine, right? And cobalt and the oxidation state was 3, so we put that in Roman numerals, and then that's the end of the complex name, and now we just write the counterion, nitrate. There you go, pretty simple. Next one, ooh, this one's tricky because in this case you have a positive 1 times 2, which means this whole thing better be a negative 2. Oh, 2 times a negative charge, it's negative 2. 2 times a negative charge, negative 2. Oh, wow. This looks like the platinum must be a 2 plus. So, and remember, if the metal is in the anion, we have to be careful. So we'll go ahead and just name the complex first. We'll say, okay, this is going to be what? We've got a bidentate glycine, right? It comes glycinate. And so we say this is a bis. And I'll put it here, glycinato, right? And then you got hydroxo. So then that would be a di. Hydroxo, and platinum is in an anion, so we call this not platinum, but platinate, right? For anionic complexes, we put that in ATE. We give the oxidation state, and then we write the counterion, in this case, potassium. So potassium bisglycinato dihydroxoplatinate 2. There we go. Next one, getting a little bit more complicated here. We see that the phosphate is a 3 minus, which means this whole thing has to be a 3 plus. Amine doesn't have any charge. That's a negative 1 times 3. That's a negative 1. Wow, so that's got to be what? A positive 1, 2, 3, 4. Wow, that looks like it's going to be a 7, right? Ooh, that's pretty crazy. So here we have what? We got a bunch of ligands here. We put them in alphabetical order. So I'm going to say we have diamine, right? And again, there's 2 M's in amine. And in this case, we've got what's next? I think the cyano. So there's 3 of those. Tricyano. And then we've got this bidentate ligand here, or sorry, ambidentate ligand here, sorry. In this case, it's bound through the nitrogen, which we will call what? That is the isothiocyanato ligand, right? And in that case, then we write, it's a cationic, so we can just write manganese. Manganese. And the oxidation state, which is really high, right? If I can write Roman numerals today, that would be nice. There we go, there's my 7. And then finally, the counterion, which I don't have room over here, so I'll put it down here. It's going to be phosphate. So that's a mouthful. Diamine, tricyano, isothiocyanato, manganese 7, phosphate. And the last one, here we go. We got 2 ammonias, so that's going to be a 2 plus. Luckily, carbonyl is neutral. That whole thing's got to be a negative 2. This ligand, right, is based on, this is the nitrito ligand, negative 1, and 2 times negative 2, that's negative 4. So in this one, it looks like it's going to be, is that going to be a 3? No, that's going to be what? Yeah, I guess it is. I can't do addition and subtraction today. I'm getting tired, sorry. So 3 plus, right? Because 5 plus 3, yeah, that makes sense. There we go. So let's go ahead and write the counterion and get it out of the way. Ammonium. There we go. And now let's put all this stuff into order. Now make sure to be careful here because that's a metal in an anion, so we need to add an ATE to the end. So don't forget that. We can write what? This is going to be carbonyl. And then we've got nitrate and oxalato. So I'll put the O first. So bis oxalato, right? Bidentates get the special prefixes. You've seen 3 examples here. And then finally the last one is going to be, it's bound through the O, so this becomes nitrito, right? And then finally, you might be tempted to say iron, but you have to use the special, remember the root here is iron, even though it's Fe, you're going to say ferrate. And that's in the reading, and again, if you can get the oxidation state, boom. So this is ammonium, carbonyl, bisoxalato, nitrito, ferrate 3. Boom, you got it. Oxidation states are really important. Make sure you review that. Make sure you know the special prefixes. Make sure you can count the charges. All that's really important. I promise you, you will have some naming problems, so be able to do those. Okay, electron configurations. You got to look at the noble gas. So here we put a xenon here, and I would say what? This is going to be 6s2, 4f14. 14, and then finally what, a 5d5. For rhodium, I'm going to go ahead and just knock this one out. At this point you should be able to do this. You have krypton, and then remember the neutral would have some s and some d electrons, but when you remove them, you remove the s. The s is first and then the d, so that leaves you with 4d6, and there you go. All right, moving along. Here we've got some isomers, right? So here we want to actually draw them out, and again, when you draw isomers, just draw the complex. Don't worry about the counter ions. And so you've got 2 bidentates, so that takes up 4 spaces plus 2 of these. That's going to be an octahedron. Stereoisomers, right? Stereoisomers are the different spatial arrangement, not different connectivity. So I'm going to keep it bound to the nitrogen, but I've got 2 of them, which means I can do my cis and trans, right? So I'm going to go ahead and do the chromium here. I'm going to draw that in the plane of the paper. At least 4 of them. I've got 1 behind, 1 front. In this case, I've got 3 minus, right? So that means that's 2 minus, that's 4 minus, and so that's 6. That means the chromium's a 3 plus. I'll go ahead and write that down because that's important, because I say label a charge, 3 up. And then here we've got what? In this case, you're going to have oxalate, right? And you did this in your lab, right? You had carbon, 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 oxygen, boom. And that's just what you did in lab. So oxalate, you should be able to draw that by now. And I'll go ahead and, I don't know, I'll just go ahead and do this one as a cis. And then you get that, boom, you got that, boom. There's our 2 oxalates. And now I'm going to go ahead and write my isothiocyanatose. And then you know this is my cis. Since this has a charge, we should label that charge 3 minus. Okay. You want a stereoisomer, we got a cis here, we should do the trans, right? So let's go ahead and draw this one over here. Very similar to the one we had before. 1 behind, 1 in front. Again, this is a 3 plus. This time I'm going to go ahead and draw this out now. We've got, again, note where those are bound. Nitrogen, carbon, sulfur. So now we've got trans, right? Which is 180 degrees apart. And now we can just throw in the carbons and the oxygens for the oxalate, right? So we throw that in. Don't forget to complete your Lewis structure. And then over here we've got the oxygens bound to a carbon, bound to a carbon, bound to the oxygen, double bound oxygen, boom. And then here we go. Draw this out. Overall charge 3 minus. Cis and trans, those are stereoisomers. There you go. Now this one down here is constitutional isomer, right? And these are the ones where you actually look at the linkage, the actual connectivity. That's really important. Again, this is a 2 monodentate ligands and a pair of bidentates, so that's going to be coordination number 6. Again, an octahedron. I'll put the iron in the middle here and draw this out like so. We should probably figure out the charge. Ethylene diamine's neutral. These guys are -1 times 2, which means in order to balance the chloride, this whole thing is -1, which means it looks like the iron is going to be a 3. So 3 plus there. I'm going to go ahead and draw my ethylene diamines. You should be able to draw those by now, the little carbon backbone. Put my guys like that. There's my hydrogen. The 2 carbons are attached. I'm going to go ahead and draw this bound to the nitrogen to get that. There we go. And I'm going to go ahead and draw these. Initially it's bound through the nitrogen, which is a nitro, right? I'm going to leave them both that way. And there we go. So now we can draw that as a 1 minus, right? That's really important. So 2 negatives, yep, that works out. So now this was bound through the nitrogen as given. So now we're going to do a linkage isomer, right, if you want to be specific about it. I've got my 3 plus again. I'm going to draw 4 in the plane of the paper. I'm just going to keep the same rough configuration to keep it simple. Draw that, and then I'm going to connect to my carbon fragment, the little backbone, boom, there's my ethylene diamine. Put 1 behind the paper. Here's my ethylene diamine over here, and my ethylene diamine over here. Bind that to the CH2, the CH2, and then the carbons are connected. I'm going to have the one in front of the paper. In this case, I'm just going to go ahead and change both of them. I'm going to just bind this to the nitrogen, double bond O, and for, I don't know, you could leave this one the same, it doesn't matter. You just have to show me that you can bind it through a different element, and then there you go. So there is a linkage isomer for both of those, and there you go. Now you could do different things where both of them are in, both of these are O. You could have one be nitrogen, one be O, and it's all the same. As long as you show me that you're doing a linkage isomer, you're fine. All right, moving along. This one's pretty quick. Here we've got a palladium complex, right? In this case, it's palladium. What, you've got 2- for the whole thing. Each of the chloros is a -1, which means that's got to be a palladium 2+. If you look at that, that ends up being a D8 if I've counted right. And so D8s are very, very happy being in the square planar geometry, so that's important. So we can go ahead, and for square planars, I mean, I told you guys the one that you really want to be careful about is that by all means the x² minus y² has to be the highest energy, because remember, if you look at x and y, where our ligands come along by crystal field theory, you can draw that orbital, and that orbital lies right on the x and y. So when you bring the ligands in, they are going to hit bang on, and that's going to be a lot of repulsive energy, which means it's going to drive that energy of that orbital way up. And so the rest of them I'm not too concerned about. You can just put them down here if you wish, and so you'll say, okay, well, that's probably going to be xy, that's z², that's xz and yz, and I'm not too worried about the ordering of these two, but I really want you to see that that is your giant gap square planar. And so here you say, okay, well, I've got 8 electrons. I can go 1, 2, 3, 4, 5, 6, 7, 8, and they occupy this lower energy cluster of orbitals, which is fine. But the moment you go D9 or D10, you're going to have to jump that. And if you jump that, you're going to have to rearrange and become a tetrahedron. And so here, you've got your 48, and that's fine, square planar all day long. And you can draw that, right? You can sit there and now draw palladium 2+. It is a planar complex, so you can just go ahead and crank that out. Overall, you need the charge, which means it's going to be 2-. Boom. Pretty simple. Again, maybe pick something that's copper 2 and do a tetrahedron to make sure you can cover all your bases for the 4-coordinate complexes. All right, we're moving along. This next one was one that I think some of you were having trouble with mechanism, and that's fine. So you only have 2 choices, right? You've got this one here, which is clearly what geometry? It's an octahedron. And you're going to be removing a carbonyl and replacing it with an OH, a hydroxyl. Pretty simple. So I'm going to go ahead and draw this. And again, it's only a couple steps. Don't make this out to be something that's more difficult than it needs to be. Got my rhodium, and that rhodium, remember, carbonyls are 0, which means that rhodium's got to be a plus if the whole thing is a plus. So I'll draw my rhodium charge here, and I'm going to draw my octahedron like this. And remember, the carbon is the one that bonds. And you can draw those, right? There you go. And you can draw the one in front here to be carbonyl, and the one in back to be the carbonyl. There we go. And this whole thing, right, is going to have a positive charge. Now, this is octahedron. There's no way, at least for this reaction, you're going to bring in that hydroxo and sneak in somewhere. You're just not going to do it. What's going to happen here, the first thing that happens when you have an octahedron, is you're actually going to kick off one of those ligands. And that's why this is called a dissociative mechanism, right? Dissociative because the first slow step, and again we said this is the slow step, it's a rate determining step, it's going to kick off a ligand, so minus CO, and you're going to get a new complex. And this new complex, again, is going to be rhodium plus. I'm going to go ahead and draw this with 4 carbonyls. I know I'm rearranging it a little bit, it's okay. And one of those is going to be out of the plane, which means we now have a pyramid. We've got 4 carbonyl ligands with the rhodium as a square base, and then you've got this one sticking up. That's a square pyramid. And I'll go ahead and write that, square pyramid, right? And you can go ahead and write octahedral over here. And you need to remember that that's probably actually not the most stable geometry. I'm probably going to flux over, right? Flux. And so let me erase that. That looks pretty bad. Sorry. There we go. All right. We'll go back over here and we'll say, all right. There we go. Flux. And then this other option then would be to have a rhodium plus, but you can arrange 5 things a little bit better to be a trigonal bipyramid. And then you would have 1 behind, 1 in front, and you'd have your carbonyl. So this would be trigonal bipyramid. And you can go back and review. And then at this point, one of these, and again, it depends on more data, but for right now, one of these is going to have to react with the hydroxo ligand. And you've got some lone pairs on the oxygen, right? So you can form a bond, either coming in here or coming in from behind that square pyramid. Regardless of how you do it, your final product has to match what's up here. And so it's going to be an octahedron. So we have our carbonyl still. And then in this case, we still have a 1 plus rhodium. And you can use a Roman numeral or a plus, it doesn't matter. Here you're going to have the carbonyl, and the new ligand, of course, is your hydroxo. Now, it's important here to do your brackets because here now you have a 1 plus metal and a negative. One of your ligands is now negative, so you have a neutral complex. So that's the mechanism. 1 step, 2 steps. Not that hard, but you have to kind of talk about it being dissociative because the first step is actually the rate determining step. That slow step is actually the loss of a ligand. Whereas in the square planar, you would actually have the attachment of a ligand. So that's how associative and dissociative differ. All right, let's move along. Making some progress here. Next one, number 7. Use your understanding with reactions. We need to add something to meet these requirements. We want to decrease the solubility of lead chloride. Okay, so when we talk about solubility, that should ring bells that we're talking about KSP. So we can write the KSP equation for lead 2 chloride, right? That's going to be an insoluble salt in water. And we're going to get lead, what? 2 plus in the aqueous form plus chloride is in the aqueous form. Now, if you think about it, we can talk about this in terms of Le Chatelier from 111. So you can say, okay, I want to make this value go down, and the way you do that is you get the reaction to shift in that direction. So if we want to decrease this, what could we do? Well, maybe we add chloride. If you add chloride, it's going to shift the reaction to reactants and decrease the concentration. And what's a source of chloride? Well, table salt, right? You could add some sodium chloride. You could add some potassium chloride. These are both soluble salts. You add those in as a source of chloride. Common ion, right? If you remember that from the reading, the common ion effect will shift the reaction back and decrease the concentration of lead. So there's one example. This one again, solubility, silver chloride. We can say, okay, well, we know the silver chloride is a solid and it's going to be in equilibrium, right? It's going to give us some silver plus and it's going to give you some chloride minus. There we go. Now, again, you would like to, in this case, you want to increase the concentration of this one. And you want the reaction to go in this direction. Well, you can't add any solid because solids are not in the equilibrium expression, so that doesn't work. If you add chloride, you're going to make it go the other way, like the reaction of above. Don't want that. And I don't know if you know a way to get rid of chloride, but I'm not going to mess with that. But maybe there's a way you can remove. If you remove the silver plus, that will get the reaction to shift in that direction. And one way to do that would be to add cyanide or add ammonia, right? And why might that be? Well, you can form a complex ion. And you will have a list of complex ions and their K values on your exam. So you could add either of these. I'll just pick the cyanide, and so you can then take silver, right, plus 2 of the cyanides, and that's going to give you silver with this cyano complex, right? And that's going to give you what? A negative charge. And that's a big KF, so if you did that, adding cyanide would remove the silver, decrease its concentration, which would make more of it go into solution, and there you go. So that would increase the solubility, right? It would pull more of that solid out of solution, or into solution rather, and shift that reaction to products by removing this one and using Le Chatelier once again. So pretty cool. Talked about both of these in the notes, by the way, so make sure to go and back and review that. All right, getting there. Just a couple more pages, so bear with me. All right, so with this one, we're going to say, okay, we've got a dilute solution of this complex. Don't try to find X on the periodic table. You're not going to find it. Just a placeholder ligand, and it gives you a spectrum with a lambda max, right? So that means if you take the spectrum and you look at absorbance versus wavelength, you get a curve that looks like that, and lambda max is the wavelength that gives you the biggest absorption. Now it says this color is red. Oh, well, that's easy. What color is that complex? Well, remember, if it absorbs red, it's going to appear what? The complement. So if you look at that, you could, Roy G. Biv, right? If it absorbs red, that means it's going to look green. It's going to appear to be green, because that's the light that is actually transmitted or reflected off. So there we go. That's easy. And it relates to the fact that, these are colored compounds. They absorb in the visible range. And so if you remove this big chunk of light around red, the color that you see is going to be richer in the color across from it, green. This next one, I think we did some of these before. So, the idea of actually calculating a value, right? And so let's think about it. So you can calculate delta O, or you could say, okay, I know that this thing is what? It's an octahedron, so I can look at how that pans out. Again, use my energy, right? Boom. And I know by now that this is z squared, this is x squared minus y squared, xy, xz, yz, and the gap is called delta O because that's an octahedron. Now, if this corresponds to red, that is a small gap, right? Small gap, because red is a low energy color. So if it's low energy, that means that this thing would be on the far left, because things on the left give you small dels. So that's really important. If you want to think about it more importantly, we can say, okay, well, it's a negative charge, so that means for this one, the cobalt has to be a 3+, which I think gives you 6 electrons, and I would say 1, 2, 3. Since that gap is really small, I'm going to jump it, and there you go. So probably going to be paramagnetic. But to answer the question, ligands on the left of the spectrochemical series give you small dels, and on the right they give you large dels because they're ranked in that order. There we go. Now let's actually calculate it. And we know that we had what? This was 700 nanometers. Well, we can calculate that. We can use the equation from 111, right? E equals Planck's constant times the frequency. We don't have the frequency, so we can convert that to Planck's constant times the speed of light over the wavelength. Easy enough. Now we just look those values up. 6.626 times 10 to the negative 34, and write the units. It's worth your time. And times 2.998 or something like that. I mean, you could even put 3 and be okay. To the 8th meters per second. Now notice the units, right? Because now you need to put the wavelength, and that wavelength better be in meters, not nanometers. 10 to the 7th meters. And I get a number that looks like, it's going to be something like 10 to the negative 19th joules per photon, right? And you're going to take that number times Avogadro's number, right? That's 6.022 times 10 to the 23rd, and that is photons per mole, right? And then remember, you need to divide it by 1,000, or multiply it by what? 1 kilojoule is 1,000 joules, right? And that, when you crank that all out, I get something on the order of about 171 kilojoules per mole of photons. And there you go. Now again, if you're doing something right, you're probably going to get 10 to the -19th, because that's a small number for individual photons, and when you multiply it by Avogadro's number and divide it by 1,000, the kilojoules are roughly in the the 1 to 300 kilojoules per mole range. If you've done enough of these, you kind of get the idea. And the bottom one I've already done for you, but I'll just remark again. You have cobalt 3+, which is a 3D, so that's going to be argon 3d6, and you just crank this out. Boom, boom, boom. Show me that you have del O, and this is what z squared, x squared minus y squared, xy, xz, yz. 1, 2, 3, and again we said if this gap, it corresponds to red, that's a small gap, so we'll jump it instead of having to suffer the penalty of pairing up electrons. And then we do have to pair one, but there we go. And so we have 1, 2, 3, 4 unpaired electrons. It only takes one to be paramagnetic, and so yes, there are 4 unpaired electrons. So this is definitely going to be paramagnetic, right? Para. There we go. That's that one. One page to go. Thanks for your patience. We'll get you through this. All right, this one gives a lot of you guys a little bit of trouble, so I thought I'd include one of these KSP equation ice type setup problems. So here we're looking at the KSP for silver carbonate. So this is a relatively insoluble salt, or partially soluble. -12, yeah, that's pretty small. You're not going to get much of that in solution. So let's go ahead and write. When you're given a K, I would urge you to think about writing the chemical equation first. And so I've got my silver Ag2CO3 carbonate, and that's going to be a solid. It's an equilibrium, right, and some water in this case, and I'm looking at the concentration of, I'm looking for silver, but remember this is going to form 2 silver ions in solution by stoichiometry, and then 1 carbonate ion. Try not to, don't be tempted to break up that carbonate. That is 1 ion, right? And so now we can say, okay, we've got the silver carbonate going to 2 silver pluses and 1 carbonate. Now we can think about the chemistry. Now we can think about how to approach the solubility. So here you're going to say, okay, I want to find the silver ion concentration and molarity. And here we got DI water. So the nice thing about the ice table, right, is that this is a solid. Remember, pure solids, pure liquids, we don't care about them. They are not involved in the equilibrium expression, so don't worry about that. We've got the silver. Now, initially, did we add any silver? No, it's DI water, so we know that's 0. Did we add any carbonate? No, it's DI water, so boom. However, we know that at this point, if you calculate Q, right, which is the same algebraic expression of K, but we have no product, so Q is 0, which means even though that K is small, Q is even smaller if it's 0, because even something small is better or higher than 0, right? So here we say, okay, I'm going to have to shift at least a little bit to products, which means I'm going to go plus 2x plus x, and so even I can do this. 0 plus 2x is x, 0 plus x is x. So these are my equilibrium concentrations, and so this is really important to note that that is going to be equal to silver plus at equilibrium, which is what we want. So keep a note of that. Let's go ahead and write out KSP. KSP is going to be equal to the silver ion concentration at equilibrium squared times the concentration of the carbonate ion at equilibrium. And I can crank this out from my values from my ice table. I'm going to get 2x for the silver squared times x for the carbonate. And that's going to give me what? Don't forget to distribute this to both, right? So it's going to be 4x cubed, and that's going to actually equal the number 8.4 times 10 to the -12. That's good. Now remember, we solve for x, but remember x is not what we want. We want the silver concentration. And so I got 1.28. I'm going to keep an extra sig fig until the end. Times -4th molarity. Now remember, we have to multiply that. So 2x is actually what we want. We want the silver concentration at equilibrium, right? That was up here. And to get that, I think, what did I get? I got 2.6 times 10 to the negative 4th molar. So there you go. There's your concentration of silver at equilibrium in DI water. Now the next question's a little bit more involved, right? You have to use the same setup, but here we're not dissolving it in water, in pure water anyway, we're dissolving it in this guy. And we've got some silver nitrate. What that means, since this is a 1-to-1 salt, that's going to be 0.1 molar silver and 0.1 molar nitrate. But you'll notice if we write the equation, right, Ag2CO3 solid going to an aqueous, we're going to get 2 silvers plus carbonate. And I would argue nowhere in this chemistry, nowhere do I see nitrate. So I don't care about nitrate. Nitrate's a spectator. The only thing I care about is that silver. And so we can begin to think about how to set up a new ice table. Again, we don't care about the solid. It's not in the equilibrium expression. But here you have to be careful. You're not dissolving in pure water, so it's not 0 like up above. It's actually 0.1 because you had 0.1 molar silver nitrate around initially. Do I have any carbonate? No, there's no carbonate. So again, Q is 0, so it's going to have to shift a little bit to give some carbonate. In this case, it's going to be plus 2x plus x, and so it's 0.100 plus 2x, and then this is going to be simply x. So now we can set up our K expression, right? We're going to say we have K SP, which again is identical to what it was up above. The equilibrium concentration of silver squared times the equilibrium concentration of that carbonate. And we can write that in terms of what we derive from the ice table, right? You're going to get 0.100 plus 2x squared times x. And if you look at that, you might be tempted to say, wow, that is going to be a bear to solve, and there's no way I can do that. Well, think about this. Remember, the number we got up here was pretty small, and we're talking 10 to the negative 12, so I bet the x is really small compared to 0.1. So I'm going to make an approximation. I'm going to say that that x is tiny. So that's going to give me 0.100 squared times x gives me 8.4 times 10 to the negative 12. That makes the math really easy, and if I solve that, right, I can solve for x, which means that I can solve for 2x, and when I solve that, I get something on the order of 1.7 times 10 to the negative 9th molar. That is crazy, and that equals the concentration of silver plus at equilibrium. And so look at that. That's like 10,000 times less soluble than in DI water. So here you can see where the power of the common ion effect, if you dump in a little bit of this guy initially, it really slows down the amount that can dissolve and makes that salt much less soluble. And so yeah, 10 to the negative 9 versus 10 to the negative 4, assuming I did my math right, that's pretty crazy. So there you go. And this relates back to the problem where we talked about adding things to either increase or decrease solubility. This is, again, just a very common example of the common ion effect, no pun intended there. All right, the last one, and then we can call it a day. This is relating to kinetics that we talked about before. And so we know that to get a rate law, right, rate law takes the general form, rate equals some constant, the rate constant, times the concentration of one reactant raised to some power times the concentration of another reactant raised to another power. And you might be tempted to just write the stoichiometric coefficients, but yeah, sometimes you'll get lucky, but don't do that. Actually look at the data. So let's look at this first example. We need to change the concentration of this one and hold the other one constant. So notice experiment 1 to 2 rather. We've doubled the concentration of nitrogen monoxide, but we've held this constant. Okay, so if we look at the rate here, the rate actually goes up by 4, which means N has to equal 2. Because if we double the concentration and the rate goes up by 4, that's an exponential relationship. That's second order. Pretty cool. This next one, we want to change the oxygen. We want to double this one, 2 times that, but we want to hold this one constant. In this case, what happens to the rate? It doubles. okay, well, if I double the concentration of oxygen, I double the rate, that means it's first order. So there we go. We've solved for the rate law. That is pretty cool. And again, if you want to show your numbers, that's fine, but you can also explain your work in terms of your thought process and write that down as well. So there's the rate law. The last thing we do is we say, okay, we want to solve for the actual value of K, which means we can plug in a number, right? I'll just bring this down here. So just pick one that you like. I think I might just pick the first one, and I'll write the rate down. So the rate equals 0.0141 molarity over seconds. That's going to equal K. And then my concentration of nitrogen monoxide, right, that's going to equal 0.0126 molar squared, right, because that's second order, times 125 molar raised to the first power, which you don't even need to write down. Now, the trick here is you have to be careful, right, because you know that rate has to be molarity per second. This one's going to give you molarity squared. This one's going to give you molarity, which means we'll be at molarity cubed, which means that K has to be in units. We need to get second, so we need seconds on the bottom. And then check this out. We need 1 molarity to be on the top, but we've got 3, so that means we need to get rid of 2 of them. So we need to put molarity squared on the bottom. And if you crank the number out, I think I got something like 71.05. And then the units are most challenging. So anyway, I hope that's helpful. Wow, I could use a drink of water at this point. That was a lot of work. Kind of a long video. I knew it was going to happen. I apologize, but I hope you can kind of cherry pick and find things that are helpful to help you build confidence in these kinds of problems. Again, if you just want to check your number, scroll around, check your number, but if you would like to have more of a guided walkthrough, maybe focus on one of these problems and watch the whole part of that problem. I hope like I said, this is useful, and I hope it helps maybe direct you to old problem sets or old group activities in class that dealt with problems that maybe gave you more trouble. So to be honest, I mean, at this point you've seen a lot of homework, you've seen a lot of group activities in class, and then you've seen this monster of a video. So I hope this helps you build your confidence, lets you go in, feel good about this exam, and really knock it out of the park and earn as many points as possible. And again, like I said, if you have questions about this, come see me. I'll be around. And then we definitely have the problem set, the pre-exam review session in the evening. So come check that out if you're able. So I hope this has helped. If you have other questions, come see me, and let's do well in that first exam. Go team.